Hello everybody, I'm Laetitia, so I'm a PhD student in computer science at the University of Bernstein, and I'm also working at NIST as a guest researcher. So I'm going to present you the research that we are doing, which is about mapping method for aligning machine execution data to numerical control. So the presentation will be separated into two parts. So the first part will be about an introduction about the standards, the problem that we're trying to solve, and the work that has already been done. Then I will talk about the methodology that we have developed, and the last part will be about the case studies, the results that we had, and the future direction that we are going. So first, we are working on the product life cycle. So the product life cycle have different standards depending on the different stage in which we are in the life cycle. So there is the design, which we are in the design we are focusing on step 18 to 24, which define the geometry of the part that will be built. Then there is the manufacturing stage. In the manufacturing stage, there is different standards. That the first one, for example, would be NCO, which define the operation that the machine is expecting to do. Then there is anti-connect, which allow to transfer the information from what is really executed by the machine. And then there is QIF, plans and results, which define the inspection once the part has been machined. So here the idea is to develop a digital thread between all those standards, so that we can facilitate the flow of information upstream and downstream flow of information. So in order to do so, there is different challenges. The first one will be to understand the link between those standards. Once we have the sync, we can then label data. So keeping in mind that there is a causality change, because, for example, the design change, then obviously the execution and the data will change too. And we also have to find a use case and adequate data in order to test what we are doing. So we have, so as I said, there is a problem of probability of the data, so find adequate data. And also there is a problem of a silo effect, because all the standards have been developed obviously for a particular stage in the product life cycle. So there is diversity of data and formats, and which is why the control information is not trivial to do right now. And if you want to develop a framework or solution to do so, it's time-consuming and expensive. So the solution here would be only to focus on the data approach, so that we want to map the different data standards and formats using a black box algorithm, so that we won't have the need of computer scientists or really specific people that will only know what they are doing. And we want to not to add other requirements for the industry. So there is already work that has been done in this area. So for example, there is OPC, UA, and Anti-Connect that are developing companies' specification, so that it allows a transfer of information between the standards. There is something similar with STEP and QIF. They are developing a mapping specification. And there is also another part which is more focused on the analysis and the feedback of the standard. So there is a methodology that has been developed, which is on the steps. So it's an methodology that represents AP242. It will allow to do analysis of the design, the product. And there is also step tools that has developed a virtual product model, and that allow to align it to the execution data. So in the semantic to do some analysis and feedback. So all those work have the same challenges, which is, as already said, the availability of the data, and all the solutions are expensive and time consuming. This is all the solutions try to solve those different problems. They are great, but still, what we want to do is really to focus on the data. So here the idea would be to develop mapping between each stages of the data, each stages of the product life cycle, so focusing really on the data. Right now we are focusing on G-code and anti-connect, so to develop a mapping that will allow to transfer information between those two standards. So to do so, we developed a methodology that will first need a data preprocessing of the two standards, then a way to back out the two offsets, so I will explain it later. And then we deploy a mapping algorithm that will allow to map the two standards, and of course, measure the error in the data that we have. So the first step is data preprocessing. So in the anti-connect data and in the anti-code inscription, we need to find in the anti-connect data the real portion of the data that is related to the anti-code that we have, so which might not be the case. We might have an anti-connect data that has multiple operations for multiple anti-code. Once we have that, we can then back out the points, the coordinates of the points in the two data sets. So we have to keep in mind that the NC code reports the overall position of where the tool should be, and it only gives the relative change from the previous position. Whereas the anti-connect data don't have, just give the actual position of the tool. So once we have those two data sets, those two set of points, we have to back up the two offsets. So why the two offsets? Because in the NC code, it's the idealized position of the machine. So we just assume that the machine will start, for example, from this point and then do all the work. Whereas in the anti-connect, it doesn't know what the part is built. So the position, the point that are reported are the position in the actual machine space. So those two spaces are totally disconnected, and we have to find ways to put the points in the same dimensional space so that we can compare it and map them together. Once we have that, we can then deploy the algorithm. So basically, we have first to cluster similar points, then to select the NC point that will be compared to the anti-connect point. And once this comparison is made, depending on the distance between those points, we can then label the data saying that, for example, this anti-connect point will be linked to this NC code. And once we have the alignment, we can then measure the error. So basically, we take the plan of the expected path of the tools, and then we take the points, the anti-connect points that are linked to this plan, and see the difference between those two. And it allows us to see the overall estimation error in the mapping. And then from that, we can then identify area of improvement and also identify source of discrepancies that might be, for example, physical problems or tool wears or. So we have developed, we have used data sets that have been developed in the NIST, the SMS testbed. So this data set is what we can say more like an industrial, or what we can find in a real industry, because the NIST SMS testbed work as we just send the design, and then there are machines that do the job, so we don't control all the experiments. We are really trying to emulate what is happening in a real industry, so we don't know what is happening. We don't know, for example, if the operator has stopped the machine or things like that. We just take the data that they give us and then try to use the method that we have developed. So we have the case study was hard sync from an avionic control box. So we have the G-code and the anti-connect data, which is the controller data that is reported. It has the pole position, the feed, the speed, and the path direction of the tool. First we have the preprocessing part. So in this case, there was a previous operation done before the actual NC code, so we have to cut it and then find the positional data. Then for this use case, we think that the tool of during the NC during the G code in the G code file, there has been different tool changes. So we have to find the tool offset for each tool change, and then from that we can deploy the algorithm. So we have to define a certain precision. This precision is due for example, the data of the controller, the speed of the data that is reported. So it really depends on the use case. And the preliminary result that we have is here. You can see it's like each point represents an empty connect point, and the red line is the expected path of the tool. So each color, I don't know if you see, but each color is linked to an empty connect point. And here we can see the number of empty connect points linked to the number of NC code lines. So we can see that there is a huge peak near the 0, which is good. So it means that it really matches the NC code and towards the empty connect point. So there is not a lot of points linked. So we can really identify which point are linked to which. And here we can see that there is errors that are due mainly to the tool change and also to error into coordinate that we include later. And so then we measure the error in the data alignment. So here the same, we can see that there is a huge peak near 0, which means that the distance between the expected and the empty connect point are low, which is good also. And here we see that there are large discrepancies. Those discrepancies are mainly due to the tool change in the execution data. And all the medium discrepancies here are either around the coordinate or discrepancies that are other discrepancies that can be due to either tool wear or other physical problems. So that might have a signature that we want to investigate later. So in future direction that we are taking, we will first part trying to develop the algorithm. So find a way to derive the tool offsets and automatically, so we won't have to have any insight. Then we will try to segment the execution data and separate it into the different operations automatically. And we are also trying to explore other coordinate space, like vectorial space, and other distance measurement, like similarity or dissimilarity measurement, for example. And then try it with a 5-axis scenario, since we only use a 3-axis machine. And then once we have improved the algorithm, the idea is to use the results to find external disruptions. So what can cause all those discrepancies that I told you. So either identifying patterns in those discrepancies or classify the error using, for example, unsupervised neural network, so that we can find some signature in the discrepancies. And we are also trying to develop our own data set, so which will be a short experiment in the NIST SMS test bed, so that we will try to control a little bit more what is happening, and also try to have a data set from a real company. And so to conclude, the goal of this work is really to map the G-code and anti-connect standards, so that we can have a downstream flow of information, and hopefully this flow could then go back to the upstream product lifecycle stages.
We have plenty of time for questions. Any questions?
So Do you do any data cleaning, data processing before you do the analysis? And if you do, what do you do for that? Especially taking into consideration that sometimes sensors may not be working properly or something.
So right now we're just doing those two steps for the data processing. So we are not I don't know, maybe you are thinking about like noises in the sensor. Is it what you're?
Yes, or misreadings or something like that.
Okay, so no, right now we're not taking this into consideration. We are just assuming that the data that we have is what a normal company might have. They might not have any insight about the noises or anything that might have caused problem during the execution. So we are really trying to, like, if I were a basic small companies, what can I do with this data without having a lot of computer scientist skill or other expertise with this data.
Okay.
So which technique did you use to measure the position of the cutting tool? The position is each axle position is reported. So which technique did you use to measure the position in it?
We just have the data from the controller. So the controller, the machine, gives us directly the position of the tools.
Okay.
So CNC controller does not have the readings of those positions instead of installing the actual sensors.
Okay.
Yeah, I was wondering if I'm not really sure how the data acquisition is formed here, but would it be possible to use time information in this as well? Because I assume you're not using it's only position data. Would it be possible to make use of time during execution for the two data sets? Match them?
Yeah, actually, we are kind of using time because we are assuming that we don't have any times in the NC code, so it's just what the machine should do one step at a time. But we have the time in the MT-Connect, but the problem is that the MT-Connect information, depending on what the controller sends you, there might be like 1,000 more points in the MT-Connect data than in the NC code. So you don't know when each change when it's from one operation in the NC code to the other one. So that's why we have to use the position, because basically we assume that since it's going from one to another, then if the points are closer to a position, then it means that it's related to this operation in the NC code, whereas when it's changed and it's closer to the other operation, then it's linked to the other one.
Yeah, there's also significant challenges within the standards community in understanding how to deal with the temporal challenges of the data acquisition. So there's latency in basically storing from the controller back to wherever you're logging in the MT-Connect agent. So even if you were to leverage the temporal data for the mapping, it might not be as consistent as you think. There's actually like operating system bound issues.
But
in reporting
is
the data.
Sequence used? Like
Yeah, the sequence.
Sequence, yeah.
Yes,
that's what it says.
yeah.
Okay.
I have a quick question. Could you go to the last conclusion slide? Yeah, so your goal statement, I'm not quite sure the final goal. I assume it's to relate downstream data back to upstream PL stages. So could you be a little bit more specific on the goal? So you want to, in a more quantitative fashion, you want to reduce time or increase the efficiency, or what's the final goal?
So, so the final goal is to have each line here represented by mapping. So the final goal is that we can have a flow of information between the stages. So once we have this flow of information, we can of course use it, for example, to have decision making in design, or to have inspection so that we can detect error before it happens. before having to do it in the extent, before having to expect the part. So here, the mapping is really focused on allowing a flow of information between the stages, and then from that we will try to leverage it to other.
So yes, and one of the things I was going to ask is, in what way the results are presented? But if I understand from what you're saying, those results are potentially stored in a database to then later be accessed. They are not presented as a recommendation to the operator or something like that. Is that correct?
Yeah, no, there are rules like that. Because really you're focusing on the data side and not on the recommendation side.
Yeah.
Later.
Yeah, just chiming in, there's a pragmatic issue where we have this test bed where we're generating data,
Yes.
yet there's no good way of reporting it in a consistent way where streams of data relate to, for instance, design information.
Yeah.
So this is a first step of us being able to release data in more consistent technical data packages. We describe that in the paper if you want to read a little bit more. Yeah.
Last one.
So, in additive manufacturing, we have our open test bed. We can do G code, and we can send the positioning there of where the laser is going to be. And then we have something that we can read back from the galvo positioning, and predict where the mirrors are pointing the laser, where the position is. But we still don't necessarily trust the galvo response, and we want to see, whether it's a camera or some other type of thing, of actually seeing the location of where the melt pool is on a platform. And so if you're looking at errors here, you're looking at the as planned, and you're trusting MT Connect to do the as executed. Are you also doing positioning from some sort of third-party external thing outside of the machine?
That's really what we decided here is that we just want to use the basics. So what we expect that will be basics in all the companies. So we don't want to add any sensor or any data. We might do it later, maybe to validate what we are doing or add other information. But for now, we just want to focus on the data that might be available.
So there's no other data that compares the MT Connect data with some sort of actual foundation location, and there's no other.
Okay, so let's speaker again.